Welcome to video 7. If you have looked ahead in the notes, you will have noticed that we will soon begin talking about two-dimensional problems. We've been so far talking about the use of the finite difference method to solve ordinary differential equations, that is, differential equations in which there is only one independent variable x. And so these are problems having a problem domain restricted to the x-axis. But in the near future, we want to begin learning how to use the finite difference method to solve partial differential equations with two or more independent variables. We will begin by solving two-dimensional partial differential equations where our independent variables will be x and y, and so our problem domain then will be regions in the xy plane. But before we get to that, I would like for us to consider one last computer project dealing with the material that we have been studying so far this semester, and I hope that in a way that this will wrap up everything. Now, let me begin with some review. One equation that we have looked at in our previous work is the following. We have d squared y, or v, it doesn't matter, dx squared plus k squared y is equal to 0 with the boundary conditions y of 0 is equal to a and dy dx of L is equal to B. And remember that we've referred to that first boundary condition, y of 0 equals A. We said that that is is called a Dirichlet boundary condition when we set a boundary condition on the value of the function itself. And then the second boundary condition, dy dx at L is equal to B, is called a Neumann boundary condition. Because it's a boundary condition on the derivative of the function rather than on the function itself. Now, you will recall that the analytical solution to this is y of x is equal to c1 sine kx plus c2 cosine kx, where c1 and c2 are chosen to satisfy the boundary conditions y of 0 equals a and dy dx of L is equal to b. So all of this is straightforward, and you have done this kind of problem before. And in fact, you've done it twice. You recall that you did it once enforcing the, I'll back up and say, the two different ways that you did it, or the two times that you did it, involved two different ways of enforcing the Neumann boundary condition at x equals L. Okay, so we considered the use of both a first order and a second order approximation for the first derivative in implementing the Neumann boundary condition. This was one of our very early projects this semester. And you might recall, actually, that sometimes the first order boundary condition would give results that seemed to be actually more accurate than those generated by the second order boundary condition. Generally, I think the second order boundary condition gave better results, but not always. But I think the point I want to make right now is that if you will go and review the notes, you will see that we did justify the statement that the boundary condition that we were calling second order accurate was indeed of second order accuracy. We derived it using the Taylor expansion. We had the one-sided derivative formula, and we showed how the error in that varied as delta squared, and so therefore that was indeed a second order accurate approximation to the first derivative. However, for the other method, the one that we were calling the first order accurate method, we really didn't justify that it was first order accurate. So I want to explore that a little more now and see what we can do with that idea. So if you will remember, what we did was the following. If the last node was node n and the next to last node was node n minus 1, and we assume that the spacing is delta, then the way that we implemented, dy dx of L equals B by enforcing the following equation. And this is, well, I should say, for the first order case, because for the second order, of course, we involved not only nodes n and n minus 1, but also node n minus 2. And if you don't remember that, please do review your notes. But for the first order case, it only involved these two nodes, n and n minus 1. And so let's complete this sentence now. For the first order case, we implemented dy dx of L equals B by enforcing the following equation. And it was the last equation, it was the last row in the matrix, and it was the following. We said y of n minus y of n minus 1 divided by delta is equal to b. Or another way of writing this would have been minus 1 over delta times y of n minus 1 plus 1 over delta y of n is equal to b. And therefore, what you would have had in your code is something like this. Mat of n minus 1 is equal to minus 1 over delta. Mat of n equals 1 over delta, and RHS, the right hand side, n is equal to b. That's what we did, and that's what we called the first order method for implementing the Neumann boundary condition. However, as I said a moment ago, we never really justified the statement that that is a first order accurate boundary condition. So let's take a moment to investigate that. Now, remember that the Taylor expansion gives us the following. It says that f of x plus delta x. Actually, I guess I'll just go ahead and jump right to the what we want, which is f of x minus delta in this case. So this will be equal to f of x plus f prime of x over 1 factorial times negative delta plus f double prime of x over 2 factorial times negative delta squared plus f triple prime of x over 3 factorial times negative delta cubed plus dot dot dot. And so if we rearrange this equation and we can write it in the following way. Let's take f of x over to the left hand side of the equation and f of x minus delta. Well, let's do it, I guess, one step at a time. So we have f of x minus delta minus f of x. This is simply taking f of x over to the left hand side of the equation is equal to minus f prime of x times delta plus 1/2 f double prime of x times delta squared minus 1/6 f triple prime of x times delta cubed plus dot dot dot. And now let's multiply both sides of this equation by -1, and so we get and not only that, actually let's just say it like this, let's divide through by negative delta. So if we get f of x minus f of x minus delta over delta, that's what we get on the left hand side if we divide through by negative delta. See, I've used the negative sign to flip the numerator, and of course the delta is in the denominator. And now I need to divide the right hand side by negative delta, and so we get f prime of x minus 1/2 f double prime of x times delta. Delta instead of delta squared, because remember we're dividing through by negative delta, plus 1/6 f triple prime of x times delta squared plus dot dot dot. And so you see then that f prime of x, if we compare the right hand side and the left hand side now, the exact value of f prime of x here on the right hand side is equal to this approximation that we're using, but the error here, this represents the error, and the leading term in the error is of order delta, and it's delta to the first power. So this justifies, this verifies that our formula is first order accurate. Now, so this is the theoretical justification, but I'd like for you to look at this numerically. And so this is our next computer project, and this, I believe, will be our last computer project on the finite difference method in one dimension. So what I want you to do is to go back and I suggest that you do this in your code where we were doing Richardson extrapolation, and you remember in that code you produced two curves. One was the curve that you obtained from the I'm sorry, the word escapes me right now. Let me take a break. Well, we what I want you to do is we were doing a procedure. You were doing a convergence analysis. That's the word I was looking for, and so you were doing a convergence analysis, and you were plotting for each value of the spacing. You would find the error in your original solution, and you'd also find your error in the Richardson extrapolate solution. And then you graphed the log of this error for both of those, for both the original solution and for the Richardson extrapolate. You plotted the log of the error versus the log of the spacing. And we got two different graphs. We found, since we were using second order accurate formulas everywhere, our original solution yielded a curve that had a slope of 2, but then the Richardson extrapolate had a slope of 4. But now we're no longer using second order accurate formulas everywhere. If I want you to use this formula right here, I want you to use this formula to implement the Neumann boundary condition at x equals L. This boundary condition right there. Okay? And of course, you've already done this once before, so this will be trivial for you to make just that little change in your code. And I want you to do the convergence study and to verify what you should expect now. Well, actually, maybe you're wondering. Let me back up. You might be wondering if the overall solution will have an error that is first order accurate. In other words, it might seem strange to you. Everywhere else in the problem, we will be using second order accurate formulas. What I mean is that when we implement the differential equation at the interior points, we will be using second order accurate formulas for that second derivative. It's only at the one point at x equals L, it's only at that one point that we will be using a first order accurate approximation rather than a second order accurate approximation. So will that mess up everything and make the whole solution first order accurate? I mean, we justified that we proved here, down here, we proved that the formula at that one point is indeed just first order accurate, but does that make the whole solution first order accurate? I'd like you to think about that. And then, as I say, what I want you to do is go ahead and do the convergence study and look at the slope of the line. And I'll just go ahead and I guess give this away is yes, you will get a slope of 1 as you get the spacing gets smaller and smaller. Just that one point messes up everything. And I'd like for you to think about why that is true. And then the second part of this computer project is for you to do the Richardson extrapolate as well. And that's why I suggest that the way you approach this computer project is by taking the Richardson extrapolate code that you already have written and just modifying it. But let me caution you. Now, and this is why I really am excited about your doing this formula, because this sort of ties up everything. This gives you a review of a lot of the ideas that we talked about in the first part of the semester. But keep in mind, you are going to need to go back and review the Richardson extrapolate ideas, because you remember that for the Richardson extrapolate, the way that you form that is by taking a linear combination of the solution calculated at delta over 2 and the solution calculated at delta. In other words, you took 4/3 of the solution calculated at delta over 2, and you subtracted from that 1/3 of the solution calculated at delta. And that when you combined them in that way, you got the Richardson extrapolate, which was fourth order accurate. But that was only true. You could only do that because the original solution was second order accurate. And the fact that original solution was second order accurate was what determined those coefficients of 4/3 and minus 1/3. But now your original solution is going to be just first order accurate. So you need to go back, look at those notes, and figure out what should the coefficients be for the Richardson extrapolate in this case. And also, once you get the right coefficients, what is the expected accuracy for this new Richardson extrapolate? So I hope that you'll find this interesting, and try not to give your classmates too much help on this. Let them struggle a little bit, because this is a good challenge for you to see if you grasp the ideas that we've been talking about. So I hope that you will enjoy working on this computer project, and that concludes the discussion of the computer project. So good luck.